Earthquakes. Earthquakes are one of the most feared of natural disasters because of the amount of devastation they can create, both in terms of building destruction as well as endangering lives. So what's happening to create an earthquake? Well, we associate earthquakes with fault zones. The San Andreas Fault in California is the one that most people in America think of as earthquake central. There's also the New Madrid Fault in West Tennessee, which historically has had some pretty devastating earthquakes. None recently, but many feel that it is overdue. But there's also many minor faults that are not associated with the major plate boundaries, but are interior to the plate boundaries. And these are usually associated with the smaller earthquakes that crop up in places you don't typically think of as having earthquakes, like Virginia and places like that. And although we still think of fault zones as being our primary source, really all plate boundaries have the potential for earthquakes, because in all of these places your rocks are under stress and strain, and that's what's ultimately going to lead to an earthquake. So what happens? Well, of course, you've got a fault zone. So you've got rocks being pulled in opposite direction. Well, at first, they're not going to move very far. And it may not even be enough to permanently distort your rocks. They may bounce back. And so you've got plastic deformation because of the bounce back. But then they move a little bit further. At this point, the rocks can't bounce back, so we start getting into the realm of plastic deformation. Think about stretching a rubber band. So now, we first pulled it, we kind of let go, it bounced back. Now we're pulling it, and we're not letting go. So we're going to keep stretching it farther and farther. Well, of course, what happens to that rubber band? Eventually it breaks. And so that's our fracture. Well, when the rocks break, you're going to get very sudden motion. Just like when you break that rubber band, you're stretching it, stretching it, stretching it. But when it breaks, it pulls apart really fast. And that's what's happening to these rocks. And that sets up vibrations. And it's those vibrations that we feel as an earthquake. Now, when talking about an earthquake, you hear information about where the earthquake occurred. And there's two main terms related to that. First is the focus. And this is typically underground and where the actual fracture occurs. So this is your breaking point. And as the picture shows, it's not usually at the surface, but someplace underground. The point on the surface, directly above that focus, is the epicenter. And this is the one you usually will hear in the news, because they'll talk about what town was closest to the epicenter. Now, how we know this is by a seismograph. This measures the strength of an earthquake. And this is an old-fashioned one, but a pin recorder will jiggle back and forth depending upon how strong the earthquake is. So that tells you the strength. If you have 3 seismographs in 3 different places, then you can triangulate the location based on the time that it took to reach each one. So whichever station got the signal first is obviously closest. And that timing, you can actually, for each location, okay, that arrived in a certain amount of time, it's got to be somewhere around there. And then your next one is over here. Maybe they got it second. So they've got it, no, it's someplace in that circle. And then your third station finds that it's somewhere in this circle. So basically where the 3 circles intersect is where the earthquake occurred. And from that we can figure out then if that's the epicenter or the focus, where the location is. The Richter scale is how we indicate the strength. And typically this is based on the destruction and how much the seismograph reacted. And the way the scale is set up, it's actually what's called a logarithmic scale. So each number on the Richter scale is 10 times stronger than the one before it. So if you had a 1.0 versus a 2.0, the 2.0 is 10 times stronger. A 3.0 is 10 times stronger than the 2.0, but it's 100 times stronger than the 1.0. So each number up, you're going 10 times stronger than the number before. So you were dealing with powers of 10. So you'd, 1 to 2, that's 10 times stronger. 3 is 100 times stronger than 1. 4 is 1,000 times stronger than 1, and so on. Now, looking at this scale, you can see really small ones aren't even felt. 2 to 4 are relatively minor. That's going to be just small jiggles. Around 5 to 6, you might have some damage, but not too much. It might just be like cracked windows and things like that. When you start getting into 7 and above, that's when you have the chance for lots of fatalities as well as major destruction. Now the largest one shown on here, 8.9, is the largest measured. They can get higher. So it can be worse than that. We just haven't measured one that's worse than that. Now, related to earthquakes are tsunamis. These are a result of earthquakes under oceans. And so what that does, let's say this is the ocean floor, is it starts a wave out in the middle of the ocean. So here's our epicenter. As it goes inland, what happens is when it gets to shallower water, it's going to start moving upward because you've got the same volume of water, but now it's in shallower land, And so as it moves inward, that same volume of water is going to get higher and higher. And so you end up with this wall of water moving inward, and that's what we refer to as a tsunami. So all of this, whether it's an earthquake on land or a tsunami in the ocean, is ultimately traced typically to a fault zone where you will have first elastic deformation, then plastic, and ultimately the fracture, which is what leads to the vibrations that we associate with earthquakes and with tsunamis.